today's first talk.
Yeah, so last time we saw a general K-theory of C-star algebra setup to define index of the signature operator or similar operators, and today I want to fill this with some kind of completeness. So I guess it's good to recall this general setup. Well, to get the index of the signature operator as an element of a K-theory group on an m-dimensional manifold, and with some fiddling that is going to live in KMS of a C-star algebra. Yeah, what was this general setup? I said we want to get an index in the K-theory some C-star algebra, which I'm really calling C-star, right? So what do we need? For this we need and secretly we're thinking of this C-star algebra, C-star as a subalgebra of the other bounded operators on which this signature operator acts, so bounded operator of the Hilbert space of forms. I mean, this was a different operator for the Hilbert space of sections or whatever bounded operator acts. So it's all complete inside the bounded operators of the space on which this acts. Okay. And what we needed was that for functions f, which are continuous and vanish at infinity of the real line, we can form the f of t, and this is going to be a bounded operator on this Hilbert space on which it acts, because f is a bounded function. And our requirement was that this f of t should be inside this C star. And actually we saw from this homotopy formula that that's all we need to define this index class. We wanted, however, to complete the picture a little bit by also constructing something which I call a kind of a fundamental class. Signature fundamental class, which would live in the K-theory of another algebra, and this was supposed to just be obtained. The index was supposed to be obtained by taking the fundamental class and taking the index map, the boundary map, in a non-side sequence in K-theory, where here I would like to have, therefore, a quotient. And there's going to be a second bigger C-star algebra, D star, also subalgebra of the bound operators of this Hilbert space on which our operator acts. And to get this, I actually need a bit more, namely that for functions chi, and we call our chi was this odd function which had value -1 at minus infinity, +1 at plus infinity. And more generally, we take functions which are continuous functions on a real line, and actually extend to a continuous function on the, well, 2-point compactified real line. Okay? For such functions, we want to have that chi of t, which is still defined because that's a bounded continuous function on a real line, that should be inside the bigger algebra t star. There are more of this kind, and so it's likely that some of them go beyond C star and live in D star. Okay. So we need this setup, and actually I was making a small blunder last time when I explained how to construct this in the homotopy picture. So recall also that there was one definition of this K-theory group as homotopy group pi m of a certain space assigned to the C-star algebra here. And I was focusing on the case that m is 0, then we had to construct an element in the space, which was a homomorphism from this C-star algebra essentially to this C-star algebra. And here this is then pi m plus 1, so we're thinking of chi 1. So I have to construct, to get an element in here, a loop in this space. So a loop of homomorphisms from this algebra essentially to this algebra. And to construct this loop, I wrote down a formula which didn't quite work because there were some extra conditions on how these homomorphisms look like. They have grading preserving. And to correct this, I'm not telling you how, but we discussed it after the talk. We need one extra thing. We need so we need this property, and we need the existence of an odd self-adjoint unitary U star, also in V star. And if you remember the constructions we made, at some point I said to make a K1 class, I have to do something invertible out of chi of d. I wasn't exactly chi of d I used, but I used chi of d, the positive part of it. It's an odd operator. And I was composing that exactly with such a u. So you saw it already that we somehow used it. And to use it, you also have to have it. Because in this very general abstract context, that's not automatic. In all the cases I had in mind, it is there. That's why I overlooked it. But if you make a very general setup, I have to assume this odd unitary to exist. Okay. With that, we can then also make the homotopy, the picture where you have to construct this loop without too much trouble. But I don't think I want to get into that today. That's the general setup. We need C star and D star. C star an ideal, and D star, and I put all of this in bound operators, L2 of forms. And we've seen one example where this works, where D star is all bound operators and C star is the compact operators, and this works again as a compact manifold, and there's much more that you can do. So you have to put yourself in a situation which is a bit more interesting and complicated to be able to develop this somehow in a more fruitful way than just getting the integer index you get by the compact operators. Yeah, if you want to fill. So my trick to make the situation interesting is we're going to start with, I will actually see two interesting situations. We start with M, which is closed, smooth oriented, of course, so it has its Dirac operator, if you also, its signature operator, if you also put the Riemann metric. But I'm assuming it has an interesting fundamental group, or maybe more generally, it has a given fixed reference map to the classifying space of some discrete group. And in this situation, we can make our life more interesting by not working with M, but with the gamma covering we obtain either by thinking of M having fundamental gamma, just take the universal covering, or more generally by pulling back the universal gamma covering here to M. Okay? So, and then instead of working with M, we can work with M tilde, which has a lot of nice extra structure. It is non-compact, that is making life complicated, but also more interesting. But there is an isometric action by this discrete group gamma, which helps us to sort out things a little bit. Okay, so we really will look at this thing here. And now we define actually, for the definition I'm going to make now, that it's closed is not so important. I want it to be complete. we know that the signature operator can be constructed for complete Riemannian manifolds with all the good properties. So closed ones or special case might be complete ones for constructions we're doing now. Still, passing to the Earth covering, it's even more non-compact than the complete thing we start with. Okay, so we have to define inside the bounded operators our C-star algebras we're going to work with. And we define one of them is called the row algebra. C-star of tilde. And I'm actually taking inside it some gamma invariant part. So we will have the C-star until the gamma, which already came up in the first talk. And now the task is to define what it is. Well, by definition, it's going to consist of bounded operators on L2 forms. And these have to satisfy a number of conditions to make them qualify to be inside this row algebra. What are these conditions? One of them is, as I indicated already, T should be gamma equivariant. So gamma acts on the manifold, so gamma acts on the functions that pull back isometrically, and we want T to be compatible equivariant for this gamma action on the functions of forms. So that's something we all understand. T should have what is called finite propagation. And maybe I'm just completing the picture. I'm going to tell you in a second what this is. And the third condition we have is that T is what is called locally compact. I'll tell you in a second what this is. And now this is going to be a star subalgebra of all the bounded operators, but not necessarily closed. Now what are we doing to get the C-star algebra? We close that. Right. So I told you that this is going to be our method, and our method. Operating. Right. Okay, so that leaves us with details to discuss. What does it mean that T has finite propagation? It means that there is an R, which is a bound on the propagation number. Such that, well, T takes a section of our form bundle, takes a form, omega, and this omega will have a certain support, which is a certain set of inside n tilde. The points where this form is non-zero, and propagation R, now it we apply T to it, and we get a new form. And obviously we say T has propagation R if the support is spread at most by R. Okay. So this is the support of T, and then we take this R neighborhood around this, and we require that the support of T applied to any omega is contained in the R neighborhood of support of omega for all omega. Well, it suffices to do this for the for the dense subset of continuous forms of compact support, then we don't have to worry about the precise definition of support. It would of course make sense in general. Okay, and this is actually the point where you, which is not normal. If we can have a sequence of operators which are all having time propagation, but the propagation is getting bigger and bigger, so that the limit operator wouldn't have any finite propagation, but it would be very close to one with finite propagation.
Should the form omega be on M tilde?
Pardon? Yeah.
Okay.
With compact support, that's what you mean.
It's the same. I mean, if you check it for what forms have compact support, it will also look for those which don't have compact support. Right? Using CAC trick, partition of unity trick, to relate the general one to the compact non-object or something, convert it at least strongly. Well, okay, and what we also have to define is what is meaning that T is locally compact. Well, the definition here is that whenever I take a function which now is continuous with compact support on M tilde, this is not only a function, it is also an operator on the L2 forms by pointwise multiplication. You can multiply a form with a function, get a new form. It's also bounded. This is a bounded function, as it's compact support, it's certainly bounded. So I can think of these, and I won't distinguish them as a multiplication operator, and therefore I can write down T composed with phi, multiplication pointwise with phi. And local compactness means that this should be a compact operator, as we discussed it last time. And similarly, if we do it the other order, first multiply with phi and then compose with let the operator T act. So those should both be compact operators inside L2 of L2 forms. And a generalization to other bundles and sections is evident. Okay, so that's the definition, and we have a task to check the properties in a second. But let me also define the partner, the D star, just to complete the picture. You can take D star to be all of the bound operators, because we have the condition that the smaller one is an ideal, the bigger one, and if you try to work out whether this is an ideal, you will fail. The finite propagation property is destroyed if you compose with an arbitrary operator. Okay. So D star, which is the structure algebra, so we're still in the definition part. Structure algebra. D star of M tilde gamma is defined to be all bounded operators in the two forms. Well, what are the properties here? Still we want them to be gamma invariant. Still we want them to be of finite propagation. Note that composition of two finite propagation operators still has finite propagation. Propagation just adds. So that's a good property for an algebra. And the local compactness is weakened to something called pseudo-locality. So, already define what that means. Where is called pseudo-local. It's a weaker condition than the local compactness, if and only if, whenever we have two compact supported functions, phi and psi, on M tilde again, and now I'm supposing that their supports are disjoint. Then we can apply the multiplication operators. One, we first multiply with psi, then we apply t, and then we multiply with phi. And I'm assuming that this guy is a compact operator. You see that's a weaker condition. If this operator is compact, then the composition with anything else is still going to be compact. So everything in C star is certainly also in D star. But not necessarily the other way around. Because,
do you really need that support disjoint? I think you want a little room between the supports. Or is it enough that the
supports are closed sets, so if they are disjoint, there is a little room between.
Yes. Is it important that you have this, or is it would phi times psi equal to 0?
We will go to an equivalent description, which is saying that if this holds, that's the thing I want to check. Something better holds, namely the thing you mentioned.
Yeah.
So we just could require that phi times psi is 0.
Yeah.
And even a bit stronger property holds, namely that if we take for a compactly supported function, the commutator of t with phi is multiplication with phi. So we call that t phi minus phi t. This is a compact operator. That's to go from here to here is really easy. To go back is not so easy. That is actually proved by Kasparovs and Kasparovs, and requires some approximation trick, among other things. So, but this tells you that your question is somehow in between those two, and also holds. And but often we're going to use the strong property, but it's more convenient to check the weaker one, obviously. So, very good. And give you an idea of why they called what they called. T could have a singular integral kernel. Actually, the Schwarz kernel theorem tells it always has an integral kernel if you allow singularity of a more appropriate general type. So it will look like we have m tilde times L tilde, and then we'll have a kind of function on m tilde times m tilde, and the operator is obtained by taking the function, multiplying with the form and integrating out one direction, and then you get a function depending on the other direction. So T f y would be with all quotation marks integral over m tilde of this kernel kt of yx and of x. Okay, that's what an integral kernel is supposed to do, and that's the corresponding operator. And this is something which holds appropriately interpreted for all bound operators on L2. Very well. Now, what does it mean to have finite propagation for such an integral kernel? The integral kernel is going to be supported in the R neighborhood of the diagonal. It only spreads that far, which is translating to the fact that we have AT being supported on this R neighborhood of the diagonal. Or if you like to think in terms of matrices, it's some kind of a band matrix, this operator. Okay. What does it mean to be, so that the equivariance, of course, some equivariance property of this kernel. So that's easy. What does it mean to be locally compact? Well, if we multiply from either side with phi, think of phi as being a characteristic function of a compact set. Then we just take out this part first, and the integral kernel is relevant only in the strip above that part. And this thing here is then somehow a compact operator. So locally, if we pick out a compact piece in this direction or in that direction, which is the same because of the finite support, we do have a compact operator. Only the global picture, because so big, makes it a non-compact operator. But if we pick out a finite bit of this matrix, then it's compact. That's why it's called locally compact. And the pseudo-locality is, if you think of this picture here, you're cutting out, well, something in this direction, but then, well, you pick a set which has disjoint support from that one, so it might be taken all the way here, and you cut out something like this corner, which is off the diagonal with this psi t phi. If these were characteristic functions of sets that disjoint, we cut out some corner of the matrix, but this will not touch the diagonal because phi and psi have disjoint supports. Okay? So pseudolocality says that, well, if you pick out some piece of this matrix which is not touching the diagonal, then this piece is a compact operator. But the diagonal is completely uncontrolled.
Is it the same as saying that the kernel has a singularity only at the diagonal?
No, because being a compact operator is not the same as being
but it's regular. Guaranteed. So if the kernel is non-singular away from the diagonal, then it is pseudo-local. That's
indeed
what you said.
So pseudo-differential operators, which have exactly the property that they have an integral kernel which is outside the diagonal function, will be pseudo-local.
So obviously I didn't understand something. I think so. The operator being, so if I pick a compact part of n tilde in the one direction, then the operator being compact does not correspond to this strip, which is relevant to being a compact subset of the.
No. This is then supposed to be itself. If we cut this out, it's still an integral kernel, so it's still an operator. And this operator, if you just throw away everything and only take this piece of the integral kernel to define a new operator, that would be the compact operator. And it's all it's just an idea, so you have to be careful with this.
So it really depends more on the function, the kernel itself, than actually the area.
No, it's not at all that this is a compact set.
No.
You should think of this as being a matrix filled itself at each point with an operator. And if you cut this out, you get a lot of operators here, and the whole thing put together would be a compact operator. If you only take this part, which is sitting here, or which is sitting here. Or for the pseudo-locality, which is sitting on a compact region outside the diagonal. So that's the idea. Beautiful idea, I guess, and we get nicely this two subalgebras. Of course, that's not yet complete, a closed subalgebra, so we have complete again to close up to get the C star algebra. And let me also remark there's a little bit of care to be taken. You could forget about the gamma equivariants, close up, and then take those operators inside which are gamma equivariant. Or you could take only those which are gamma equivariant and have all the other properties and then close up. And obviously, it's not clear that it's the same. Right? Mm-hmm. So, if I want to be precise, this is a really the precise definition I want. The other thing would be something slightly bigger. Good. So, there are the algebras. And then we actually make two, before we come to this properties here, another remark or a proposition. So, we saw that we're interested in the quotient of D star by C star. Well, the first thing I want to observe is that also already inside here, this algebra is isomorphic to the same thing, log and gamma, on the quotient. Why is this? Well, if you look at our conditions and also have a picture here, any element in D star outside the diagonal, it has exactly the same properties as C star has. Right? So we can take some kind of we can take a partition of unity to cut out a very small neighborhood of the diagonal part of this operator and D star, and the rest, the difference between the old operator and that one, is going to be in C star. And if you do this equivariantly, you also live in the gamma invariant part. So why is this? Because for every t in V star, gamma tilde, there exists, and actually also for all epsilon greater than 0, there exists a t epsilon in V star, gamma, and tilde with propagation of t epsilon smaller than epsilon. The propagation is the support of all these numbers r, which we shot there. That's just cutting down and just concentrating on the part of the diagonal, such that t minus t epsilon is in V star gamma. And it is obtained via kind of cutting out a neighborhood of the diagonal of this kt. So that's the idea, and you can just write it down in terms of compression with a partition unit.
So what is it with property? I can't read this.
The propagation
Propagation length than epsilon.
Probably can't read it. Still can't read what I told you. So it's meaning that this integral kernel is contained in the epsilon neighborhood of the diagonal. And this gamma equivariant.
So that the gamma is now at a different position doesn't mean anything. So before the gamma was upstairs? Okay.
Sorry. So we can use a compression via conditional unity trick to concentrate on the essential part, which is still in V star, and the difference to the old thing with everything outside the diagonal, which is in Z star. Okay. And what does it mean? Well, T epsilon being so closely concentrated near the diagonal and being gamma equivariant is a lift of an operator which acts on the quotient M. As long as epsilon is so small that the covering is trivial on epsilon neighborhoods. 2 epsilon neighborhoods of the points downstairs. So this property here, the propagation property, this implies that T epsilon is a lift of an operator on M. For this we need epsilon small enough. And actually to be precise, I'd better say here maybe M is compact such that we have a small enough epsilon such that all balls of radius 2 epsilon are trivially covered when we go from M till the 2. So let's say M is compact. Otherwise you have to play tricks, so you can actually go beyond the compact case. But let's focus on that. Well, you see a general operator on M tilde, it doesn't even make sense to say it's a lift of an operator on M. Only if it has this locality property, it makes sense. But then we can achieve this inside the quotient, everything is a lift. And vice versa, everything downstairs you can compress to the diagonal so that you can lift it. And this property shows.
I mean, purely formally, isn't an equivariant operator the same as a lift of a non-equivariant?
No. Because it's possibly spreading out things too much. So,
I mean, you take a section, lift it, get an equivariant section, apply the operator, it's still an equivariant section, it comes from something downstairs.
But not every function upstairs is an equivariant function. And the operator has to act on everybody. So, let's say it's an exercise to you to check.
No, I see.
Work this out. I guess if you think of it in terms of Z actions, and we have just the points of the integers, then an operator, so M tilde is equal to Z, and M is point. The covering is a trivial covering, but it's perfectly okay. An operator Here's a matrix, an infinite by infinite matrix. Here's somehow the diagonal of this matrix. And being Z equivariant means this matrix is invariant under shifting in the diagonal action. Okay? That's the same as being Z equivariant. You first move the point here, then you apply the operator and move back. So you have to be able to shift the matrix along the diagonal with the diagonal action. So here we apply any J's. But to be a lift of an operator on M, you have to be a diagonal operator with a fixed number. So it has still to be invariant under shift the diagonal action, but it has to be sitting on the diagonal. It has to sit on the diagonal. And you wouldn't know. I mean, that's the canonical lift of the operator downstairs, and you wouldn't put it off diagonally.
The point is the operators don't act on lifts of sections because these are not L2.
That's one thing.
Yeah. This I understand.
But in this sense, it looks as if you have some operator on M which has, let's say, finite propagation R or something. Then if you lift it, the propagation becomes smaller. I mean, we say it's concentrated on the diagonal, so propagation.
No, well, here propagation doesn't really make sense on the manifold which has.
Right, but I mean, here, for example, you say you make the propagation very small, then it becomes a lift of an operator below. So
yes. And the operator below has also very small propagation. Has propagation epsilon as well. So I'm claiming you can only lift operators of very small propagation in a canonical way. And the trick is that modulo C star, every element in this class has a representative which really has a small propagation. So liftable operators
have small propagation.
Lift. And we should maybe say here an operator is liftable in a sensible way only, but then, so if and only, if it has sufficiently small propagation, such that you can just, in this picture, think of the operator downstairs as one which has small support in the diagonal and you just unroll it, whereas if in downstairs it's kind of mixed up, you don't know how to unroll it upstairs. And vice versa, the things upstairs come from downstairs if they have small propagation. So that's why this is isomorphism algebras. And clearly it is then also, there is an isomorphism on the K-theory groups. Tautology, and let me mention only here that why something is called partial duality. This is the same as the K homology of the space M, and now it's a little debate to be done. How do you define the K homology of a space M? We as topologists would say, well, we take the K-theory spectrum and then there's a homology theory associated to it. Atiyah, I think, had the idea that K homology should somehow be given by a generalized version of elliptic operators. Which is mine. Which he never made really precise, but it's made precise in K-theory terms, like Kasparov. So one way to define that would be to say this K of the algebra of continuous function from M, comma C. And now, of course, the homotopy theory definition and this definition don't look exactly the same, so there's work to be done to check that they are the same, which has to be done by others. And this partial duality picture, it's really not very close from looking at the definition of the cycles here to see that it's the same as the definition of the cycles here. A very small modification. So it's not a mystery to see that this K-theory group of this C-star algebra is this K group, or this pair of this algebra, which is the K homology of M. So we get something quite nice out of this definition. Suddenly, one of the players we want to work with, maybe this one, is something we actually know quite well as a topologist. knowledge of M. But you wouldn't care so much. The general idea is also good.
So is the point here that if you have a closed manifold, then all these notions which are related to geometry, like the propagation speed, disappear because any operator has finite propagation tautologically.
Not a certain rule in compact manifold, yes.
Yes. So this is then.
This is the other thing you have to use here, but actually you don't need it because you could make a version without propagation, and the quotient of the two will still be the same, or the same trick. But so this is later. You have to check. Yeah, I guess that's a good remark. We should make some reality check. Can we say something in examples about the algebras we just constructed? And so it is indeed a good idea to check what is C star of M. So let's say gamma is equal to 1 and M is compact. Well, let's see. Who's my target this time? Who has an idea what this is? What do you think? Certainly there are some operators. Right. So,
compact.
right. So what we don't need to worry about is the invariance, and we don't need to worry about the propagation because it's compact. So what is left is this local compactness condition. So what is a nice compactness supported function on a compact manifold? Any function. So for instance, a function which is constantly equal to 1. So it's compact. So we have to also check that 1 times b is compact, which is a condition on p and tells you that all compact operator. And of course, because 1 is not there, if M is not compact, it's getting more interesting for the non-compact manifolds. But here, the case we had done last time is actually included in this picture. It's almost included. D star is almost never really computable. That's a kind of strange creature you can't write down in other terms. It's what it is. Except for M is a point.
Is it true that it's somehow the closure of the algebra of pseudo-differential operators of
No,
it's
bigger.
a fault.
It's bigger than that.
Is it separable?
No. It contains L infinity because those operators commute with every multiplication operator, and they have propagation 0 because they're multiplication operators, and that is not separable algebra. So if M is not a point, you're really getting something quite big.
And what about the C star? Is that separable?
That's separable. M is compact, it is.
Yeah.
And if you talk about M tilde gamma, it's also. So let me actually do this as a remark. C star M tilde gamma. Now, still M is compact. That's isomorphic to C star of reduced of gamma. Insert the compact operators on separable Hilbert space. And the idea behind that is M tilde. I mean, we have to think about L2 functions on M tilde. We have to look at operators on this guy. M tilde is a disjoint union of take one fundamental domain and translate it with all the group elements. In general, that's not precisely right because there's some measure 0 problems, but if you talk about L2 functions, these measure 0 overlaps don't really count. So the L2 functions on this are really L2 functions on some fundamental domain times gamma, which is L2 of this fundamental domain, insert the little L2 of gamma, and then you have to work out this C star reduced of gamma were the operators on here, which are gamma, no, sorry, closure of the translation operators by gamma. Here this picks up all compact operators on that from the compactness property. So take this idea to work out that this is really true. The isomorphism is not canonical though, it depends on certain choices. It turns out that what it does in K-theory doesn't depend on those choices. Okay. So up to K-theory, we can think of this as the K-theory of this, and the K-theory of some algebra tensor with the compact operators is the same as the K-theory of the algebra itself. So here we have the K-theory of the reduced C-star algebra of gamma coming in. So another thing I mentioned at the beginning is showing up in our picture. C-star of m tilde gamma is actually rather better controlled also. Now some more facts. Under continuous maps, so we have the map M to some other space X, and all should come with reference map in gamma. C star, these algebras, C star algebras are functorial. This functionality, so we get an induced map, C star of M tilde gamma to C star of X tilde gamma star, and it's compatible with inclusion in C star. And if we map further, it also works. Well, if you make the appropriate choices for the map F, this is really functorial, which of course doesn't make sense, because if you make other choices, you screw up the functionality. However, what is again canonical is that whatever you do, the effect on K-theory is always the same. So we get maps between the C-star algebras, which depend on some choices, but as soon as we apply the K-theory functor, everything is completely canonical and everything is entirely functorial.
Is it the case that, I mean, it's better that there's some KK equivalence between these algebras, or is that
We could also try to do that. But as we have even maps of C-star algebras, there are of course all these KK elements. Now, I haven't checked whether the KK element is well defined, but I think it is. On the other hand, some of these algebras are not separable, and KK is a bit less pleasant to work with, so maybe we stick to the...
But you said the map between the KK is well defined for the KK element.
Well, to define KK, often you say the algebra should be separable to start with.
Yes,
so
but for the C,
that's why using KK is a bit... Okay, so it was one fact, and actually relying on another fact, in the same sense, these algebras don't depend on the bundle. So I used the bundle of forms. I could have used the sections of the spinor bundle. The algebras are not the same, of course, but they are isomorphic, with some isomorphism which isn't quite canonical, but whatever it does on K-theory is canonical. So it's sufficiently canonically isomorphic that I can drop this notation. This requires a little bit of technical maneuvering. Actually, we should replace our definition by something slightly different, which doesn't have any effect on all the computations we do to get this right. It's a stabilization which we have to do as often. C-star word to get things right on the nose. Very well. So that's all nice. And now we want to check these properties. really are in a situation that indices and algebras, this indices of signature operator do make sense. Covering with the gamma action, this gamma covering. That implies that all continuous functions vanish at infinity. F of the signature operator is indeed in C star into that. Okay. And same thing for the other ones we need. Continuous functions, 2-point compactification. We plug those in, and chi is in C star. And the machine verse, the general set. Right. But we have to discuss the U as well. Maybe I'm skipping it. Maybe talk about it a bit later. Why not? Well, we know this Fourier inversion formula for these operators. So that's a key ingredient here. Or maybe first, gamma invariance is completely clear. Everything we do there, these are these lifted metrics. So the group act by isometries, which preserve the orientation, and then these constructions we do of the signature operator clearly is some metric thing, so it still is preserved by this isometric action. And so whatever we will do is gamma equivariant from start to the end. Gamma is isometric. And the finite propagation thing, for that, I'm using the Fourier inversion formula for f or chi. What was that? I asked you last time, but now you all remember, I guess. So do you remember?
Integral over the Fourier transform to some line chi t.
Really, that's it. Okay, now observe f. We do this functional calculus, which is continuous for the subnorm here. So we can replace f by nicer functions as long as we stick in a dense subset of this. So we can take Schwartz functions, functions which are smooth, not only continuous, and which decay very rapidly at infinity. Even if you multiply their derivatives with polynomials, it still goes to 0 as you go to infinity. So f in Schwartz, suffices by continuity argument, because we have to show some statement about a C-star algebra, so we can always work with approximations. Now that means that the Fourier transform is also a Schwartz function. So it decays very rapidly as we go to infinity. By the way, there's a principle: if f is really regular, very smooth, then f hat is really going fast to 0 as you go to infinity. If f is going fast to infinity, f hat is going to be quite regular. So here we have both. F hat is Schwartz, so that can be approximated by f hat r supported on minus r. So up to a very small error, this is the same as the integral that we use is f part r of t e to the I dt. And now, we might as well have said this integral which went from minus infinity to infinity. This function is supported in minus r, goes from minus r to r. Outside the function is 0, so the integral can be cut like that. And there we now need that this has propagation t, absolute value of t, so the whole integral has propagation at most r. Just by integrating, summing up operators, propagation less than or equal to r through r. Propagation smaller than r. T is smaller than equal to r. And so we conclude that this operator here, we call this fr of d, has propagation only r. And as we did r go to infinity, this approximates better and better that, so approximate better and better that operator, and we have the convergence mean. Okay, that is this.
So why does the e to the I over, why does that have finite propagation? I mean, if I think about this in terms of the power series that defines it, then you get terms of higher and higher propagation.
Yes.
Well, first of all, because E is unbounded, it's not a good idea to try to define this in power series. It doesn't converge at all. So it's a property of these wave kernels, which is not easy to establish, which I mentioned last time as a key property without proving it. So this is this theorem which goes back to Chernoff. It's an important ingredient which we use freely here. It would be a worthwhile exercise to prove it, but there's even more analytics.
It must be classically very well known.
It is classically very well known.
Because it physically is completely intuitive, absolutely obvious.
But if you have a wave and you have a speed of wave, which is encoded here in the coefficient 1, or t, so that's why it happens. But of course, that's physical intuition. Intuition is not precisely what we mathematicians want to use. Okay, so I think I have 2 minutes left to also discuss the local compactness. Maybe before doing that, let me just make the argument works also for chi of t as chi hat t is well, what was my principle? I said the faster this function decays, the smoother the Fourier transform is going to be. So this doesn't decay at all as you go to infinity. It has these two limits, which means that this is not smooth at all. Now, however, you can analyze what's happening by making an explicit calculation for an explicit function. And you might know that the constant function, value equal to 1, has a Fourier transform, a delta distribution at 0. So there is a serious singularity happening. However, we can compute this. It has singularity only at 0, which is under control. We can check how singular it is. So it's singular at 0, but all the rest is exactly like f hat. In particular, we can approximate it by something which is smooth and rapidly decaying and can be cut off to something of compact support. So outside 0 is like f hat, and which means that the argument for the fine propagation just works the same way. Okay. That's a thing which is always written down by rote, this part. And he somehow always says the local compactness is a consequence of elliptic regularity without spreading it out. So, you see the last minus 2 minutes. Spread it out.
You started 3 minutes late, so you have
Last one, that's great. So be locally compact, and I'm claiming we saw this already. So what means if I in continuous function with compact support, on M we should multiply f of d with phi, and then see it's a compact operator. And you can pick whichever side you want, because if something is compact, its adjoint is also compact. That is f of d adjoint is f bar of d, so that's under control. We can pick the side we want to multiply with. The other one follows by looking at the adjoint. So let's pick I positive f of d. That is our operator from L2 falls on n tilde. Then we do f d, and we get a form on n tilde. But as we discussed last time, if we take f of d and apply d once more to it, it's the same as applying putting d into t times f of t, which still is a bounded function. So even if we apply d once more, we will have an operator from L2 to L2, which is continuous. And by elliptic regularity, this implies that f of d itself goes to the first doubler space W1. Okay? So this factorization here, we've seen last time, and it works the same way. Same argument, the operator in this space was just defined as low L2 function, but then also d of them is in L2. Now, let's have this already. Now, second thing we want to do is we multiply phi. If phi is a C1 function, which is good enough, again by approximation argument, we can as well multiply W, the double F1 function with phi, and get a double F1 function here. That's a continuous map, and first multiplying and then including, or first including and multiplying of course commutative. And what is happening now is that after multiplying with phi, we land of course only in the W1 functions which are supported on the support of phi, which is a compact subset of n tilde. So we can replace the inclusion of W1 into L2 by the inclusion of W1 into L2 for some compact manifold which contains this piece which is relevant. And then we have some non-compact manifold n tilde, but here we have support of phi, and everything is only happening on support of phi, and the technical trick would be to cut out some region, take the double, so this inclusion is the same as the inclusion of W1 into L2 for a compact manifold. Because everything is after multiplication with phi in the support of phi. And this is compact by relish as the relevant piece of n tilde when you support phi is compact. So in the end it's actually very easy argument. It's good, reasonable to omit it. And you see the compactness of this thing here is certainly necessary to get this done, because on non-compact manifold this is never a compact map, this inclusion. And let me finally tell you why it also works for E star. Pseudo-local. So if we look at phi compact support functions on the tilde, with support phi intersected with the support, the distance between support of phi and support of psi bigger than epsilon. If they're disjoint, there is this epsilon there. Then phi chi t psi is, what is it, phi, we do the integral over chi hat of d e to the I of t, and then psi so we take something which we cut down to the support of phi, then we do something to it, which is this linear combination, this integral kind linear combination of all these operators. All of them are nice except for if t is equal to 0, there's some singular thing happening, and then we apply phi. But the support of this and of this are different, so really we can leave out the integral from minus epsilon to epsilon here, because that moves the things here only by epsilon, which is cut away when we apply phi to it. So this is the same as phi integral. So everything except for this integral from minus epsilon to epsilon, I have phi. And that's okay, because now the singularity is gone and it looks exactly like an f of t hat function. Okay? So the argument we did before works. Now, that is a convenient thing, it's easy to check. We would try to check the commutators, it's much harder. But I'm now macho at times, so I certainly need to stop here.
Okay, let's take, so let's